All right, this is the 3.7 video, part 2 of the curve sketching. We're looking at this number 4 for the function y equals x times the square root of 4 minus x squared. We want to identify any intercepts, relative extrema, points of inflection, and the asymptotes if they exist. Now, there are no asymptotes in this one either. You get asymptotes when you have x's in a denominator of your original equation. So the very last one we're going to do in this video will have that situation. And we want to use all of this information along with any sign diagrams about the first and second derivative to sketch the graph. This one, though, has a hint that we need to consider the domain, because when you're dealing with an even root function, you don't want to have an imaginary answer underneath this radical. You don't want a negative answer. So we need to make sure that 4 minus x squared stays greater than or equal to 0. Now, the problem with that as our domain is that that's a polynomial that has a power greater than 1. So you really need to factor that. This is a 136 skill. Find what are called the critical numbers for this. So that would be -2 and 2. And then if you remember from 136, you would place those on a number line. And this is to check to see if your domain is true or false in each side of these numbers. So this would be -3, 0, and 3. You plug them into the 2 plus x and the 2 minus x. And we want to be greater than or equal to 0. So if we plug in -3, that's a negative and then a positive, because -2 minus negative x would be 2 minus -3, so that'd be +5. So this is an overall negative sign, so that's not what we want. Then we would have 0 plus 2 plus 0 is positive. 2 minus 0 is also positive. That's an overall positive sign when we multiply, so that's a good region. And then 3 plus 2 is positive, and 2 minus 3 is negative, so that's an overall negative sign. So that's how you find the domain of an inequality when you have a polynomial that is bigger than degree 1. So it looks like our domain is only -2 to 2. We can include them because we can divide by the 0. Not divide by 0. We can take the square root of 0. So let's look at the intercepts. So if we want to find our intercepts for this part, we need to set the original function equal to 0 to find the x-intercepts. You would set both parts equal to 0, so definitely 0, 0 is an intercept. We would set the square root of 4 minus x squared equal to 0. Square both sides, you just get 4 minus x squared equals 0. Add over the x squared, and we would take the square root of that and get plus or minus 2. Which makes sense because that's when we would equal 0 if we plugged in 2 or -2. So -2, 0, and 2, 0. To find our y-intercept, you plug in 0 for all the x's. So this ends up being 0 times the square root of 4, which is 0 times 2, which is still 0. Okay, so now we know our domain of our function, which is we can only graph things between -2 and 2. We have 3 x-intercepts and 1 y-intercept. So to find our relative maxes and relative minimums, remember we need to take the first derivative. So f prime of x, or we can just call this y prime since they didn't use f of x. Y prime, though, is going to have to be a product rule because you have an x times something that has a square root with an x. So if we let the first part of that be f of x, so that'll be x, the derivative of that would just be 1. If we let g of x be 4 minus x squared to the 1/2, because that's the square root of all of that, then g prime of x would be 1/2 parentheses 4 minus x squared to the -1/2 times the derivative of the inside here, which is -2x. So that -2 and that 2 in that denominator would cancel, so this just ended up being -x over the square root of 4 minus x squared. So that's the derivative of g. So then remember, a product rule would mean we would take the derivative of the first times the second, plus the first function times the derivative of the second. And we can write this 4 minus x squared to the 1/2 if we want down there. So then if we combine these things, so I'm going to draw a little arrow here. if we combine things, we would have y prime equals, I'm going to write this as a fraction too. This is square root of 4 minus x squared over 1 plus x times negative x would be negative x squared over the square root of 4 minus x squared. We would need to get a common denominator so that we can multiply or add these two fractions together. So I'm going to multiply top and bottom of this fraction by the square root of 4 minus x squared. On top, that'll just give me 4 minus x squared, because a square root times its another square root that are identical just cancel out the square roots, because you get the thing squared. And then minus the x squared that's on top already on the other side, all over 4 minus x squared under a square root. So y prime, once we've got it all simplified down, is negative 2x squared plus 4 over the square root of 4 minus x squared. Okay, so then we have to talk about the critical values that come from this so that we can determine whether or not we have things that are going to let us have maxes or mins. So remember, for critical values, you let the top equal 0 and solve for that. So I would subtract 4 over, divide by negative 2, and then I would take a square root. So this becomes plus or minus the square root of 2. For the bottom, x equals negative 2 and 2, because you would have to look at that, solving that equal to 0. They're undefined values, but they're not undefined in the original function, so they are critical values. So you have to remember, the only time this causes problems and you would not use them as critical values is if they were undefined values in the original function. So now we're going to make our sign chart for our increasing, decreasing. So we have 4 different critical values, and you want to put them in order from least to greatest. So negative 2, then negative square root of 2, then positive square root of 2, and then 2. We want to pick a test value. Now we don't actually go, so let's make a note here, and maybe blue. We don't pick anything to the left of negative 2, and we don't pick anything to the right of positive 2, because our domain, remember, of our original function was only negative 2 to 2. So this graph does not go forever from left to right. It's going to have stopping points, and that's because it had a domain that was smaller than negative infinity to infinity. So we're going to pick maybe negative 1.7, maybe 0 here, and maybe positive 1.7. Remember, you plug these numbers then into your derivative, and I've already done this on my calculator to save time. And then I got that this first one, it comes out negative, the second one comes out positive, and the third one comes out negative. So that means we are decreasing, increasing, decreasing. Decreasing to increasing means we have a minimum. Increasing to decreasing means we have a maximum, as long as those values exist in the function. So those are our maxes and min. We'll want to find those ordered pairs. So remember, you take the number that happens at that point and you plug it back into the original function. So y equals negative square root of 2 times the square root of 4 minus the square root of 2, negative 2 squared. So that's a lot to write. So this becomes negative square root of 2 times, that would be negative square root of 2 squared is just 2, but it's 4 minus 2. So this becomes square root of 2 times square root of 2. So this is actually negative 2. So this ordered pair, and that one is the minimum. So let's go back up and fill it in on the chart. Our relative minimum from this one happened at negative square root of 2, comma, negative 2. Okay, so let's find our relative maximum point, because all we'll have left is the point of inflection, since there are no asymptotes from the original function. So if we plug in the square root of 2 to the original function, you're going to get a similar answer, except this time it comes out to positive 2. So this would be our relative max. Sorry, this screen does not want to stay where it's supposed to. There we go. So square root of 2, positive 2. Okay, so the final thing we have to find before we can do the curve sketching is the point of inflection. We also know that there were no asymptotes in the original equation, so we're going to have to take the second derivative. Now, unfortunately, it's going to be a quotient rule this time because our first derivative ended up being, so I'm going to highlight this. This was the first derivative. Okay, so when we go to take the second derivative, which I'm going to do over here, we're going to be doing a quotient rule. So the top was negative 2 x squared plus 4. So top prime is just negative 4x. The bottom is, remember, square root of 4 minus x squared. So the bottom prime would be 1/2 4 minus x squared to the negative 1/2 times the negative 2x. So again, it's still the negative x over the square root of 4 minus x squared. Okay, so then we have to do our y double prime. So we have that it's the derivative of the top times the bottom minus the original top times the derivative of the bottom all over the bottom squared. Okay, so we're going to have to work this out. So I'm going to write everything as top as a fraction. So it's negative 4x square root of 4 minus x squared all over 1. I'm going to go ahead and try to distribute some of this. This is a negative times a negative, so we're going to be doing a positive x to distribute all this. So it's going to end up being still negative 2x cubed and 4x. Okay, and then that is over the square root of 4 minus x squared. All over this part squared would just be 4 minus x squared. Okay, we're going to keep working this out until we get a nice conclusion. We'll want to get a common denominator on the top by multiplying top and bottom of this again by the square root of 4 minus x squared, which would then give me a negative 4x times just 4 minus x squared, since the square roots would cancel, minus 2x cubed plus 4x all over the square root of 4 minus x squared all over 4 minus x squared. So then looking at what we have left, we would combine everything we can on the top. So this would be negative 16x plus 4x cubed minus 2x cubed plus 4x. And that would then reduce down to 2x cubed minus 12x on the top. So, and then that is going to be over. Where people have a lot of trouble here is this bottom part. We would have this part would be over the 4 minus the x squared that was on top with it, and then we're going to times by the reciprocal of the bottom. So this part right here was just my scratch. So my final y double prime is 2x, and I'm going to go ahead and factor this, x squared minus 6 over 4 minus x squared times a square root of 4 minus x squared. So it's a pretty nasty second derivative. Now, for the points of inflection, where we have to check, right here on the top, our possible critical values here are 2x equals 0, so that would just be x equals 0. X squared minus 6 equals 0, so that'd be x squared equals 6. X equals plus or minus square root of 6. So we do need to check those to see if they actually make sense in our domain, because I don't know square root of 6 off the top of my head, but it's actually bigger than 2. So this part doesn't make sense since our domain is negative 2 to 2. That's outside of our domain. The bottom, we also get the 2 and negative 2 again for both parts. Because of the x squared being squared, it could be either positive 2 or negative 2. So we have 3 possible points of inflection. And remember, we're not going to be doing anything beyond negative 2 and positive 2 since our domain of our original function said we don't exist beyond those points. Okay, so I'm going to be doing a test value of, say, negative 1 and positive 1, we're going to plug this into the second derivative. To save time, I've already done that, and I got a positive for the first one and a negative for the second one. So that's concave up on this side and concave down on the other side, which means that is a possible point of inflection. And we already know the point 0. 0, 0 was that point. So not only is 0, 0 an x and y intercept, it's also the point of inflection. So let's write that down on our chart, and then we'll be ready to graph this one. So some of these are much more difficult than any of the ones we had on the test, but that's because when you're doing homework, you have a lot more time to go through, hopefully, and see all the little different levels of how difficult some of this can be. So we're going to graph this now, and I'm going to graph it close to the top because otherwise I won't have room if we have room up here. And we may not. So let's graph it at the bottom. Sorry, this computer's really slow because there's a lot of ink on the page. Okay, so I'm just going to make space before the next problem. Okay, so if I'm graphing the one up above, so this is number 4 still, we had the following information. We had an x-intercept at -2. We had an x-intercept at 0, 0. And we had an x-intercept at +2. And our domain was stuck between those. We had a relative max at square root of 2, which is about 1.4 something, and then 2. So 1.4 up 2. And then we had a relative, so this was our max. We had a relative min at negative square root of 2, so that's about negative 1.4, and then down 2, which I'll have to put a tick marks over there. And that was our min. 0 was also the point of inflection, so not only is it an x-intercept, but it's a point of inflection. And remember, our sign chart went decreasing, increasing, and then decreasing, which also makes sense with our concave up and then our concave down. And we do not extend this beyond this because our domain, remember, was -2 to 2. Okay, so that's the end of that one. The last one that was in the notes, I wanted to change to one that actually has an asymptote so you could see this. So I'm actually going to change this equation to one that's a fraction. So I'm going to change it to 5 minus 3x divided by x minus 2. Oh, they didn't like that. Hang on. Let's put it in a parentheses. 5 minus 3x divided by x minus 2. There we go. So we're going to look at how do we do these same steps if we're dealing with a fraction instead. So the problem with fractions is that they also have undefined values in the original function. For example, here, the domain of this original function is all real numbers except for +2, because x cannot equal 2, since that would make us divide by 0. So we already know we have a vertical asymptote. Anything in the bottom that doesn't cancel out with anything on top that causes that is going to be a vertical asymptote. So it's going to be at x equals 2. I like to rewrite these in descending order, especially since the top's not. So that's -3x plus 5 over x minus 2. So your vertical asymptote had to do with what you had in your domain that you couldn't use. The horizontal asymptote has to do with long division. If x minus 2 can divide into this, then that means we have a horizontal asymptote. So x goes into -3x -3 times. You could multiply the rest of this out and then change the signs, because that's what we do in long division, and you get a remainder that you can no longer go into. So this right here is what we call the horizontal asymptote. So it's y for horizontal equals -3, because remember y equals means your height stays the same. So we have two different asymptotes in this one, and that was back a review from 136. To find your x-intercepts, you set the top equal to 0. So negative or 5 minus 3x, either way you want to write it. I would add over the 3 and then divide by it. So 5/3, comma 0. If you want your y-intercept, you plug in 0 for all the x's. So that's 5 over -2, or 0, comma -5/2. Okay, now that we have all of those things, we're ready to talk about what the derivatives tell us, which is our max mins and our points of inflections that are possible. So we have to do the first derivative of this. And because there's both x's on top and bottom, we do need to treat this as a quotient rule. So the top is 5 minus 3x, or -3x plus 5 if you want to write it the way we did a minute ago. So -3x plus 5, that means top prime would just be -3. The bottom is x minus 2, so bottom prime is just 1. So for the quotient rule, it would be the derivative of the top times the bottom minus the top times the derivative of the bottom all over the bottom squared. We work out the top, that's -3x plus 6 plus, because this is a 1, so that's a -1 we're distributing, so plus 3x minus 5 all over x minus 2 squared. So y prime ends up being, the x's cancel on top, so it's just 1 over x minus 2 squared. The problem is our critical value here, or what we think it is coming from an undefined value here, x equals 2. There's no x's on top. Since that is not in our domain, it can't be a max or min. In fact, because it's also an asymptote, it means that you are going to have just a vertical dashed line there that you don't cross at all. So that means we have none for relative max and none for relative min, because we didn't find any critical values that weren't undefined in the original function. And then we do still go ahead and take the second derivative to see about concavity. So f double prime. And again, we can do the sign chart. It won't hurt to do the sign chart on each side of this for the first derivative. We just know it's not going to be a critical relative max or min. So this would be 0 and 3. If we plug those into the y prime or the f prime, this would be a positive, and this one will also be a positive. So it's always increasing on both sides of that asymptote. And then for f double prime, we can actually do this a little bit easier this time, because this is 1 times x minus 2 to the -2. There's no x's on top anymore. So if we just do the power rule here, this would be -2 x minus 2 to the -3 times the derivative of the inside, which is just 1. So -2 over x minus 2 cubed. Again, this can't be a point of inflection because we already know it's an undefined value, but we can still talk about concavity on both sides of it. So it's not going to be a point of inflection because it is undefined in the original function. Anything that's undefined in the original function can't be a max min or a point of inflection, but we can still use it to help us figure out information. So 0 and 3 again, but this time we're plugging them into the double prime. So if we plug in 0, that will be -2 cubed, which would be negative, and a negative on top, so that's going to be a positive. So this is concave up. If we plug in 3, that'll be a positive on bottom and a negative on top, so that's a negative. So this one's going to be concave down. So the sign charts will still help us even though this is not a point of inflection. So none. To be a relative max or min or a point of inflection, the point actually has to exist. Okay, so now I'm going to graph this one. When you have an asymptote, that's usually the first thing you want to graph and start out with those. and then your intercepts. Okay, so I had a vertical asymptote at x equals 2, so that's a dashed line. I had a horizontal asymptote at y equals -3. And then I had x-intercept of 5/3. So that's 1 2/3. So 1 2/3 is about right here, as close as I can get. And then I had a y-intercept at -5/2. So that's -2.5. So that's down about here. So what you notice is that this graph is kind of hovering along its horizontal asymptote. It's increasing towards these 2 points, so notice going uphill, and it is concave up. On this side, we don't have any points, but I do know that it's also increasing, so that means it's going to be going uphill like this, and it's concave down, which means it should be facing down like a downward parabola, so it is. So that is the graph there, except it won't let me draw in between. So there we go. Okay. And that is the end of the 3.7 section on curve sketching.